Hello, class. I know it's a snow day. Unfortunately, they don't give me any more days to work with what I got, so we're going to go over mass spec today. I'll probably go into more of just background, go into more of the slides since, I don't want to push you too hard. As long as I cover the key points that I have on the little, lecture synopsis, that's the important things to remember. But I'll go into a little bit more background of how mass spec actually works. Maybe you know, maybe you don't. Maybe you'll learn a little bit something more. So with that in mind, sit back, relax. We're gonna go through some mass spec stuff. So these are my slides from my organic spectroscopy class. So if you want more of this, more background, more work with this, maybe if I can get enough people together for a proper class, I'll teach this. I like teaching this. It's fun. Fun is relative when it comes to organic chemistry, but it's more puzzle, less memorization. It's more like open book test kind of fun where it's like, oh, as long as you know where to look and how to interpret things, it doesn't have to be hard. But okay, so what does mass spec do? So breaking down through the theory, some of the instrumentation, most of which won't really cover how is that actually applied, unsaturation index, and some other stuff. You've already seen the unsaturation index a little bit. We'll hit it over again because this is where we can really use it. So a mass spec is a way to create charged ions. We create a charged ion, typically a molecular ion. It's going to detect this mass and correlate its mass over a charge ratio, given as a m, which is the mass, over z. So now most masses will just have one charge, so any number over 1 is itself. But that doesn't have to be the case with all techniques, as we'll see in a bit. But typically it creates a charged ion. There's many different ways to create a charged ion, and then we'll analyze that charged ion. Depending on how we create it, the molecular ion can then fragment. And then as it fragments, it's going to create both a radical and a cation. And we're going to detect all the charged fragments. And based on how this fragments, we can determine things like the molecular formula and some of the structural information. The techniques we use will control, to some extent, what we can determine. So, any mass spec has 4 steps. Vaporization, which is getting the solid or liquid into a gas phase in a very high vacuum. Ionization, which is creating ions so we can detect. Separation of the mass by some method or another, and then detection. So the sample needs to be turned into a gas phase under a very, very high vacuum. The idea being, just like in if you remember back in Gen Chem when we talked about the cathode ray tubes, they had to pull a very high vacuum on those cathode ray tubes or else they wouldn't glow. If there's gases in there, the gases will block the electrons. Well, same way. If there's a lot of molecules, it's going to block the flight of our particles as we shoot it down towards the detector. So we need a very high vacuum so there's not a whole lot of molecules. We can look at atomic or molecular level ions, not bulk, but small amounts of things. So we must introduce a charge. Otherwise, we're not going to be able to detect this. Then we have to separate these one way or another in order for them to be detected. Otherwise, you just get a clump of everything and it's going to confuse the detector. So, I'm going to go through a couple different ionization methods. While most people will use mass spec as just an extra tool in their toolbox, there are some schools that will focus entirely on this. Purdue has an analytical chemistry department that is world renowned for its developments of mass spectrometry techniques. Basically, they've developing new techniques, new ways. They're better understanding some of the fragments and how they form. And so there's some that we won't talk about now, but called the McLafferty rearrangement, where you basically form a six-membered ring in space where a hydrogen transfers from one side to the other side. It's not an actual six-membered ring, but it's like a near six-membered rings with the bonds, and it just hops over from a carbon, a CH, the H hops from the carbon to a ketone that would essentially be 5 bonds away because of how it can fold itself in space to form a near six-membered ring. McLafferty rearrangement, known after a chemist by the name of McLafferty that worked at Purdue. But okay, enough bragging. One of the methods that is often used is electron ionization. It's a hard ionization method, means we hit the atom with a lot of force. Generally speaking, we use what's called a nebulizer. So you turn your compound into a liquid. You maybe dissolve it in a solvent, and you run it through a nebulizer. We've all heard of a nebulizer before that we use as a way to distribute medicine to sick people sometimes. So basically, you run high pressure through like a dispersing thing, like basically a high pressure through a small pipe, and there's a little bead that blocks it, and as the liquid hits it, it shoots into little tiny aerosol-sized particles. And then it goes into a vacuum, so it's just aerosolizes our liquid. These then, under the vacuum, they will evaporate and they form into the gas phase. Then, why it's called electron ionization or electron impact, we use an electron beam to essentially shoot it. A sniper rifle that basically shoots an electron and knocks an electron off of the molecule, creating a radical cation. Now, since this molecule is tumbling through space, it could form any matter of rearrangements. Basically, the electron doesn't have to hit the same spot. Places with large amounts of electron density will probably get hit more often, but there's a variety of different places that can be hit, depending on how stable the radical is, depends on whether we see fragmentation, where the radical goes one way and leaves a cation going the other way. Now, one of the neat things about electron impact is that if you hit it with the same strength beam, and there's an average beam strength that most people use, it creates a distinctive pattern of fragmentation that if you create a database of various compounds, you're going to see the same fragment pattern for this compound, 3,4-dimethoxyacetophenone. And you could take an unknown, hit it, get this pattern, and then compare it with a computer database to a whole bunch of known structures, go, oh, it's this, without having to do a lot of work. Now, typically, the highest upfield peak is the molecular ion. The highest upfield largest peak will be the molecular ion peak. So this one, 180 is M+. And that is the same mass as the molar mass of this compound. This is a radical cation. And then we're going to see, you could see bigger peaks further downfield over here. I don't know, it's further upfield, I guess. Down this way. But the size of the peaks is just the percent abundance. As the detector detects these ions later on, it's how many of these guys do they see? How many 165 peaks do we see? How many 137 peaks? How many 109? Depending on the stability of the cation and the radical and where they got hit, depends on which peaks will form. So 165 is we're losing a methyl group, either cleaving here, or cleaving here, cleaving here. There's lots of different methyl groups we could lose to form 165. So this one is a particularly stable one. We are allowed to resonate that carbocation through the ring. And so we see a lot of 165. But the farthest to the right peak that's the highest is our molecular ion. Now, a softer way is chemical ionization. Instead of shooting things with the electron beam, we introduce a radical onto that, a cation onto that by throwing some sort of charged gas. So we ionize hydrogen gas to form gaseous protons, or ionize methane, where the methane gas absorbs that proton to CH5, or ionize ethane, same way. And basically these things then run into our compound, glom on some way or another, and then when they come down, we see no fragmentation. So on the same compound, instead of seeing the 180 peak, we see 181. We see a bigger peak, 209, which is we've added the ethane, or 221, where we've added a propane plus a hydrogen. So, actually, that's not propane, that's C3H5 off. But so we've added heavier peaks, much heavier peaks. And so, like, we're seeing these different radical species adding on. This is for when sometimes your molecular ion won't show up because it's very unstable. So chemical ionization is a way to make sure we get just a molecular ion peak. Now there's other ways, like electrospray ionization, where we use the charged nozzle as we shoot out these droplets. These droplets evaporate and get various, but much like in the Millikan oil drop experiment, we can have various different amounts of electrons. So as this acidic spray evaporates, we're going to have droplets with a variety of different charges, and so we're going to see a pattern of charges. So this furthest one is a peak of mass with 9 charges. This is a mass with 10 charges, mass with 11 charges, and based on the how far apart these are, we can figure out, well, what charges are and what must be the monocharged peak, which we do not see. This is often very useful for large compounds like proteins that will fragment like the dickens. This will not cause any fragmentation, but we will instead see just multiple charges. And there's other ways to vaporize, like laser desorption ionization, where you shoot a laser and that, as it gets hit by the laser, it explodes into the vaporization. It's one of those high energy ones. But there's also MALDI, which is a matrix assisted. In this case, you put a specialized solid that absorbs the majority of the laser energy. It explodes and it takes your compound with it. So because the matrix absorbs most of the energy, you don't see nearly as much fragmentation. So different ways, if it's not easy to get this into there and we don't want to see a lot of fragmentation. there's also how do we separate these masses? So we have a variety of different masses all flying through space, going to slam into the detector approximately at the same time. And it's constantly going. It's just a never-ending stream of ions. So how do we separate these variety of different masses? Well, one method is called the quadrupole. Basically, quadrupole means 4 poles, and we create 4 parallel rods. We create a voltage overlaid with a radio frequency potential. The idea is that by varying the potential, we can vary what ions get through. It's like a gate where most charged ions will be deflected into the rods. Basically, we're denying so many ions and they all slam into the wall. But we set this mass can go through. So typically the range is only 1 mass per charge, but we say this mass can pass through. And so we measure how many of those pass through in this second, and then we vary it and flip it up, how many pass through in this second, how many pass through in this second, and just by constantly cycling, we'll check all the mass ranges. Which it seems like it would take very long, but we can cycle it very fast. And you've got to remember, all the masses are trying to get through at once and at any given time. Because we're just constantly pumping species in there through the nebulizer. So by seeing that, we're saying, oh, I get out of 1,000,000 particles in this second, 100 of these particles are 180. Out of 1,000,000 particles, 150 are the 165. Over 1,000,000 particles, 10 of them are these. And so by keep on passing through, we can check all the voltages. None of them are this mass. None of them are this mass. That's the standard way most people do. There's a time of flight method, which is basically a long tube. This detector is essentially a long tube that says heavier masses will move slower than lighter masses. So every particle will have the same momentum, which is mass times velocity. So heavier mass means lower velocity. And sometimes it will even reverse it back. So they'll shoot down to the end, stretch a rubber band, and then shoot back to the detector, which is on the other side. But it allows these guys to separate based on how long they're flying. The lighter molecules will reach the end first, and the heavier molecules will reach the end last. And there's another one called an ion trap. Very similar to the quadrupole, but it's basically a circular chamber. The main advantage of the ion trap is that if you want to analyze a really dilute peak, a really dilute fragment, how do you get more of it? Well, this ion trap essentially captures the ion of use, fleeing everything else in to the side, and allows it to build up. And so if you get 10 of this key ion every second, well, we build this up for 100 seconds, and now we have thousands of these ions. And then you could then do further analysis. There's various techniques where you can run a mass spec on a mass spec. So you take out one specific fragment and then hit it again with another electron impact and see what happens. We hit it again and see how does this fragment. And by seeing that, we can understand, oh, this fragment is actually made up of these molecules. And so people who try to study these systems to death might use this to figure out, oh, this unknown fragment is actually an isopropyl group or something else. What is this group actually? So by building up this possibly dilute compound, we can build it up to large enough quantities that we can study it. But for the most part, we use quadrupole. Here's just a picture. Here's the quadrupole. The 4 poles go through, and everything, boom, 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 hits there except for what we allow through. There's a time of flight, so it gets shot through. We hit there, we reflect it back, and it swings into the detector. Just a long, long tube. And then the ion trap, the circular trap that everything else gets flung into the walls, and we capture the key mass and then eventually push it through. So one of the things we'll see, the largest, most upfield peak is usually the molecular ion peak. It may not always be present, but it's usually there. One of the key things here is it's common to have several small peaks, 1 to 2 mass units beyond that. This is due to isotopes. You gotta remember that unlike most other techniques, we are looking things on the atomic level. When we're looking things on the macroscopic level, isotopes don't really matter. But on the ionic level, if you get a guy with 1 isotope, he weighs a little bit more, and we'll be able to detect that. So, +1, it's like, so I have a carbon-13 in there, or carbon-14, or I have 2 carbon-13s. When we look at the spectrums, the tallest peak is the base peak. It's the most stable radical cation, or stable cation. And all peaks are just fragmentations, rearrangements, or neutral losses. We don't have to justify every peak, and in this course, we will not be justifying most of those peaks. So don't worry about that too much. So, okay, yeah. The molecular ion is useful for determining the molecular formula. Yes, we might use some other techniques like NMR to help confirm the molecular formula, but we can get the molecular formula from this. The n+1 peak abundance will correlate to the sum of the abundance of all the isotopes present times the number of atoms. So, example, C13 is usually 1.08% abundance compared to C12, and deuterium is 0.0115% abundance compared to protium. So naphthalene, which is C10H8, would have a 10 carbons times 108 and 8 hydrogens times 0.115, so a n+1 peak, which is 10.9% the size of the molecular ion peak. There's a 10% chance, or close to 11% chance, of finding at least 1 isotope in this compound. So if you're looking at 1,000,000 molecules all at the same time, you're going to have what? 100,000, 110,000 of them having at least 1 isotope. Now, the n+2 peak is typically either from oxygen, sulfur, but really the key thing is the presence of chlorine, copper not so much, silver not so much, and bromine. Where we're really going to focus on in organic chemistry is chlorine and bromine. Chlorine, 37, is about 32% abundance, meaning it's close to 33, but it's a pretty big chunk. Bromine is it's like 97% chance of finding an isotope. It's basically what happens is if there is a bromine or a chlorine, you can have a really large n+2 peak. And in fact, if you have more than 1 bromine or chlorine, this n+2 peak can be larger than the molecular ion peak. For example, if there's 2 bromines present, you're going to see n+2 peak, and an n+4 peak that has a ratio of 1 to 2 to 1. But so, by just looking at the mass spec and seeing, oh, I got a huge n+2 peak, I might have a bromine present. If I have a huge N+2 peak, that's 1/3 of the size of my mass peak, I might have a chlorine present. This one bromine would be about the same size. So, the other thing we can tell by looking at the molecular ion is how many nitrogens are present, approximately. There's an interesting rule that's called the nitrogen rule. That if you look at every single mass in the periodic table, count the mass of any single molecule, any neutral molecule with a nitrogen will have an odd mass. You make it charged, this rule will break. But any neutral molecule with an odd number of nitrogens will have an odd mass. If you think about it, the atoms with an odd mass can typically make an odd number of bonds. The molecules with an even mass can typically make an even number of bonds. Nitrogen breaks that rule by having an even mass of 14, but making an odd number of bonds of 3. Because of that, anytime you have a single nitrogen, or 3 nitrogens, or 5 nitrogens in a molecule, as long as the molecule is not directly charged, it will have an odd mass. And so if you see an odd mass for the molecular ion peak, you have an odd number of nitrogens. Now if you have 2 nitrogens, you can't tell that right away. But typically most compounds will only have 1 nitrogen unless they're really, really big. So the molecular ion peak is always even unless we have a nitrogen present. So that's something you can determine right away. So, as I said, so if you have the molecular ion peak and a N+2 peak, that's a 75-25 ratio, or you have an N+2 peak of a 51-49 ratio, where they're just below each other, then you have a chlorine or a bromine. Now, how do we determine the molecular formula? We're not going to go too much into this, but there is a rule that says, a place to start. Take your molecular formula, your molecular ion, and divide it by 13. And that will determine the maximum amount of carbons that could possibly get. So you take 13, so you have carbons, and then you add hydrogens until so 13 is carbon and hydrogen, and you add extra hydrogens to fill in the rest of the rest of the mass. And then that is just one possibility. Then you can exchange one of those carbons and some hydrogens for oxygens or nitrogens or any other functional groups. So we're going to use IR and NMR that can help us, so we don't usually have to determine the molecular formula entirely from just the mass spec. So we're not going to worry about that so much. This is not an organic spectroscopy class. But one thing we will do will help us is the unsaturation index. Remember, we talked about this last chapter. It tells us the number of pi bonds or rings present. So it's Cn, H, 2n plus y plus 2, and then OX, and then NY. So the number of carbons, you'll subtract half the number of hydrogens, as well as half the number of halogens. We add half the number of nitrogens, half the number of borons, and add 1. So largely it's usually just number of carbons minus half the hydrogens plus 1. But if you have nitrogens, we have to add. Halogens, as I said, take away one bond as well. They count the same as hydrogens. And while we won't typically see boron, boron counts as a nitrogen because it can make 3 bonds. But generally speaking, this, once you have the chemical formula, will help determine us how many rings, how many double bonds we'll have present in there. That should be able to match things up. Should help us simplify things. Could we have a carbonyl? I don't know. We'll see. We better have at least unsaturation index of 1. Is there a triple bond? Well, we better have unsaturation index of at least 2. I'm going to skip through this one, but there's an even-odd electron rule that says when we see a standard radical fragmentation, the new mass is always, if we, it always switches from even to odd. Odd number, odd electron. So, depending on how it goes. Oh yeah, so the molecular ion peak always starts with the even mass. When we kick off a radical, we're going to switch one way versus the other. Like we lose a neutral molecule. Yeah, I'm not gonna worry about this. Here's some various fragmentation patterns. Here's the McLafferty rearrangement I talked about earlier. See, 1, 2, 3, 4, 5, 6. 6 atoms, and we see a rearrangement to see this unusual fragmentation. So it kicks off ethene that you wouldn't normally expect. But so, okay, I just want to look at this. So, now the fragmentation can serve to hint at the structure that for example, key fragments will always be present if we have certain functional groups, such as monosubstituted phenyl group always will give a 77 and a 51 peak. As long as you have a benzene attached to something else, you should get a 77 and a 51 peak. All benzenes will lose this fragment and make these 2 peaks. If you have a benzyl, which is a benzene connected with a carbon, directly to a carbon, so you have a C, you always get a 91 peak and a 65 peak. So if you see those 2 peaks, you're like, oh, and I have an unsaturation index of 4, which would be 3 double bonds and a ring, you know, I have this functional group there. Other few things you can look for is like loss of water, loss of hydrocyanic acid, loss of carbon monoxide, or loss of CO2. These common mass losses come from rearrangement to form neutral losses. If you can see these guys, you know, oh, I got these functional groups in here that can easily be lost. Like CO is a carbonyl. HCN is a rearrangement from a nitrile. H2O is a rearrangement loss of an alcohol. CO2 is a rearrangement loss of a carboxylic acid. So being able to interpret these guys and see that will help us pick out some of the pieces there. So just looking at a couple spectras. So you see, I just want to look at this 106. There you see not much of an M plus peak. So we know there's no chlorine, no bromine. See a 91, we see a 65. There may well be a benzyl radical in there. There may very well be a benzyl cation in there. So 106, it starts neutral. It starts even, so probably not a nitrogen. That's just some things I can take away just in an instant. Do I need to justify what I lost there? No, you probably could. We've lost the mass of 15, so we may have lost a methyl group. But do I have to justify it? No. And this is just me finding, oh, here is the possible structures. And here's the unsaturation index of each. I think it's actually C8H10. There's another one with a molecular ion peak of 98. A pretty decent size M plus peak, M plus 1 peak, but still not very big. So, just looking at this, we've lost 15 to get down to 83. We've lost, let's see, another 14 to get down to 69. So, loss of a methyl, loss of an ethyl, another 14, loss of a propyl, loss of a butyl, to go from here to here, all those peaks. But I don't need to justify all these. But it does tell me probably not any nitrogens, probably not any chlorines or bromines. You can, as I said, this is more unsaturation stuff. We don't need to worry about that. Now, 91. We don't see the molecular ion. I've told you the molecular ion because fragmentation is way upfield. So, it's odd. So there is a nitrogen present. There's probably at least one. Now, there's at least one. See, so here's some just various possibilities. We can either have these compounds or these compounds if I have N3. So I'm not going to worry about that. Please note, if you're trying various structures and you have a negative unsaturation index, that structure is impossible. So remove that from all possibilities. This unsaturation index of 0 just means there's no double bonds. But negative, that's impossible. That knocks off that on the realm of what can happen. But that's all I wanted to show. That's all I wanted to show. So, looking at a mass spec in the future, when you see a big M plus 2 or think about, could I have a bromine or a chlorine? When you see an odd peak, could I have a nitrogen? We may be looking at some of those in the future when we look at some of the NMR stuff as well. I try to throw in a couple, one, maybe two problems that use either mass spec or IR when they come up in a chapter, because that's what I like to do. But this is what I wanted to go over today. I know it's 40 minutes. Hopefully you got a little bit better appreciation of this. But okay. That's all I got.